My name is Bryce, and under the supervision of Professor Dylan Liu, my Capstone project investigates V2G integration for residential PV battery systems. In terms of the contents of this presentation, I'll start off by introducing the project and its motivation, then I'll talk about the methodology, then summarize the key findings and subsequently drawn design recommendations. Then I'll conclude by summarizing the project's original contributions and a personal reflection. So to start off, I'd like to give some contextual information outlining the technical challenges the grid is facing, the case for V2G functionality, and introduce the project-specific system. So rooftop solar and PV and EV ownership are growing rapidly across Australia, and Australia actually has one of the highest per capita solar installation rates in the world. This abundance of solar, however, causes problems in the form of a temporal mismatch between the peak PV generation hours and the electricity consumption hours. So the home batteries are rapidly expanding in residential applications to address this problem. However, they do come at a large capital cost. So the case for V2G, therefore, is to repurpose existing EVs at a household to function as a flexible battery source, so absorbing the surplus PV generation and discharging back during the high demand periods. So the project in question for this project is in the form of a case study of a real Sydney home. So the project currently has 18.5 kilowatts of rooftop PV, two Tesla Powerwall 2 home battery units, and a Tesla Model Y EV. Data logs from the real system will be used to replicate the system in a MATLAB simulation, and V2G functionality will be integrated and evaluated. The methodology of the project spans 5 primary areas. So starting with the simulation framework, a 3-stage approach is taken, where firstly the simulation figures will be measured against the real data logs to validate the accuracy of the simulation first. So that's stage 1. Then the EV will be introduced with unidirectional start charging, making up stage 2. And finally, bidirectional charging ability and V2G functionality, which is stage 3. In terms of the energy flow to and from the home battery and the EV, this will be directed via an algorithm which was chosen as the linprog function in MATLAB, so linear programming. The system was therefore formulated as a constrained optimization problem with constraints which the solver must adhere to. In addition, battery degradation was also modeled as a key part of this study, evaluating the state of health and capacity loss over the simulation horizon, and that is compared to the battery's respective warranty bounds. Sensitivity analysis was also conducted on 5 parameter groups in order to identify the conditions under which V2G produces the most meaningful benefits. And finally, the results were synthesized to translate the findings into a set of practical design recommendations for households considering V2G integration. Firstly, let's have a look at the results of the baseline scenario. So under the assumptions shown at the top of the slide, with V2G, the results yielded an 87.5% reduction in grid import, a plus 7 percentage point increase in the self-sufficiency figure of the system, increasing from 92% to 99%, and a corresponding increase in the solar self-consumption and reduction in the net bill. Looking at the results of the full horizon simulation results, we see that there are varying degrees of performance gains from V2G depending on the application. So with 2 Powerwall home batteries, the 27 kilowatt hour scenario, the storage is actually sufficient such that adding V2G functionality adds no benefit in terms of the self-sufficiency and the net electricity bill. However, when we look at scenarios of reduced Powerwall capacity, we can see corresponding increased benefits in V2G functionality. For the 1 Powerwall scenario, which is 13.5 kilowatt hours, V2G produces a 5.5% performance gain in the self-sufficiency, and for the no Powerwall scenario, this is 17.6%. So similar benefits are observed in the net electricity bill. However, we must also note that the battery capacity loss also increases in these scenarios due to the additional cycling. So these particular performance figures are under the assumption of the baseline simulation scenario parameters. However, in parallel, a sensitivity analysis on these parameters was also conducted. So this was to identify optimal scenarios which a user considering V2G adoption could keep in mind to maximize the benefits. And these are summarized on the next slide. There are three primary conditions revealed by the study, starting with the stationary storage sizing. So as shown on the previous slides, in scenarios where the stationary storage is already sufficient, enabling V2G will not really provide any benefit in terms of the self-sufficiency. However, in scenarios where the stationary battery is undersized or non-existent, this is where V2G offers meaningful benefit. So secondly is the vehicle availability window. So sensitivity analysis results showed that availability during the solar window, so i.e. During the final few hours of sunlight in the day after the stationary battery has been fully charged, this availability was extremely important to harness the benefits of V2G. So specifically, a sharp drop-off in the performance was observed when the vehicle was made unavailable up until the hours of 3 p.m. and 4 p.m. So this window is actually very important. The last point is the charge headroom available in the battery. So when the vehicle was made to travel long distances daily or required to charge to a high SOC each day, the performance gains of V2G were limited as there was little headroom to discharge the battery to power the home. So this kind of implies that V2G will be most beneficial in urban applications where daily commute distances are relatively low and the vehicle can be made available for extended periods of the day. Now, in terms of what was original about this project, firstly, it's the fact that it was verified against real operational data from a physical installation. In contrast to other studies which are purely theoretical, this study was actually grounded in real data rather than being hypothetical. Secondly, the project identified and formalized three conditions which must be met and satisfied for meaningful V2G benefit, as outlined in the previous slide. Thirdly, the degradation study was evaluated as a side study within a real optimized operational context, which reflected the actual charge and discharge behavior verified against real system data. So this is in contrast to other degradation studies which tend to be standalone and may use simplified or idealized charge profiles. So the degradation results here are therefore more practically grounded. Now, looking back and reflecting on some of the key lessons I learned from this project, firstly starting with the project management and structure. It kind of sounds generic, but for a project of this scale with so many inputs and data points, it was easy to feel stalled and frozen and unable to know what to do next or even where to start. But I found that by breaking down the project into manageable stages and also having a constant backlog of tasks really helped to keep up progress and stay on track. The regular meetings with my supervisor also helped me reflect on the progress I've made and clearly setting out the next steps. Secondly, there were a few assumptions I had made along the way which I wasn't aware of at the time and I needed to rectify early. So these assumptions were in the simulation window I initially selected from the operational data, which a while later I found would be incompatible with the three-stage approach since I wasn't able to isolate the EV data. And the battery degradation model, which I initially chose, was actually incompatible with the specific battery chemistry of the EV in question. So that was later rectified after consulting a researcher in the field. But in both cases, I was reminded of the importance of being aware of the assumptions being made and also the bigger picture before diving in. And this skill is just as important as technical implementation. So to conclude, the study was a challenging but rewarding project, and I would like to thank my supervisor for supporting me along the way. So the central finding of the study is that V2G benefit is conditional on the application, but it can be maximized by satisfying the recommended three operational conditions. V2G functionality can be positioned as a practical substitute to stationary storage, and thirdly, while it does depend on the application, battery degradation generally sits within the manufacturer's warranty. Future work could extend to the study to include real-time modeling using MPC formulation and additional research avenues such as multi-household grid interaction and thermal battery degradation. And that's all. Thank you for listening.